So on behalf of the Celeste collaboration, it's really an honor to give this keynote. Celeste is an ambitious project. In simple, what we're trying to do is to take all telescope data that exists in the world and create one list of all stars and galaxies. Simple. So it's fairly ambitious. So you certainly, one institution cannot solve all problems. So it's a collaboration between Berkeley Lab, UC Berkeley, Julia Computing, MIT, and Intel. So this is a classic big data analytics problem. One of the things that you really need is a supercomputing center. If you can solve a problem on your laptop, it's really not quite big data. So the key element here is the NERSC supercomputing center, which is up on the hill. It's at Berkeley Lab, and all of the analysis was done on this facility. NERSC is DOE, the Department of Energy's production HPC and data facility. Over the last 40 years or so, we've supported over 6,000 users across a range of different domain science areas. I think it's fair to say that NERSC has a fairly solid reputation in the community in supporting HPC workloads. But big data, data-intensive science, data analytics are certainly new, relatively new. So we are trying our best to make sure that our supercomputing resources can do a good job at supporting data analytics at scale. This is my, I guess, favorite list of top analytics problems at NERSC. This is the reason why I work at NERSC as opposed to at Google or Facebook. And I think one of the most interesting things about this list is, or what we do at NERSC is, that we work at all scales in science. So Celeste is number one on the list. It aims at processing all data corresponding to the entire sky. There are problems corresponding to the entire universe, so determining the cosmological constants. And then all the way down to subatomic physics, we have problems at all scales. So for example, looking at planetary scale phenomena, climate change, and finding extreme weather patterns in large climate data sets. Extracting knowledge from all scientific literature, so it's a text mining problem. Looking at neuroscience data and determining a functional connectome. Looking at microscopy data of different modalities, and then creating an automated procedure for retrieving quantitative information from large stacks. That's an important problem in bioimaging. We certainly have problems in genome assembly. I believe Kathy Ellick may have already talked about the algorithms they are developing for sequencing, say, the human genome in a few minutes. But once you're done with sequencing, the question next is, what do you do with it? So precision medicine or precision agriculture are the kinds of problems that we care about in the DOE. And then finally, designing synthetic materials. So if you care about a highly efficient photovoltaic cell or a material that can absorb CO2 from the atmosphere, then how do you go about the process of designing an efficient material? Experiments like the Large Hadron Collider have been around for a while. They are certainly extremely data intensive. So certainly looking at the entire history of that experiment and automatically finding patterns or anomalies is where the challenges are. So there's a certain blog here, and you can read up on more details on these specific problems. Now Celeste, for me, is at the top of the list for a number of reasons. I think the scale of the problem is really interesting. So we want to process hundreds of terabytes of data. It turns out that inference at that scale is really hard to do. So you need a sophisticated statistical procedure to pull it off. And Jeff is going to talk a lot about that. But then you do need hardware. And that's where NERSC computational platforms come into play. So right now, this is sort of a snapshot of our facility. For this exercise, we're going to be using the Cori system. So this is a new Cray XC-40 machine. It's a 30 petaflop class system, has about 9,600 Knights Landing nodes, and it's number 6 on the top 500 list at this point in time. Apart from just doing compute on this machine, it is really quite important that you are able to load data efficiently. And conventional file systems, Lustre and GPFS, are frankly not up to the mark anymore. So we do use a big SSD pool called the burst buffer, which is 1.5 petabytes in size and is able to support I/O rates of 1.5 terabytes a second. Now, increasingly, while the HPC community has had a fairly stable software stack, the stack in the data space is much more in flux. So when we think about data, we think about capabilities that span data transfer, data access, workflows, data management, and visualization. But frankly, I think all the buzz is in the analytics space right now. So I'm going to spend a little bit of time on what's happening in the analytics space. So I would say that at this point in time, Python and R are definitely well established. If you have a degree in statistics, chances are you know R. if you're a scientist, chances are that you've been fiddling with Python. So those are well established, and we try our best to make sure that these tools work well on our HPC machines. Spark and Julia are experimental at this point in time. So we've been looking at Spark quite carefully, and through the Celeste project, we've now looked at Julia quite carefully. So they are certainly on their way to maturity. Tools like Mathematica and MATLAB we certainly need for legacy reasons. I'm not sure how well they're going to scale in the future, but there are many people who still just want to run these on a single node, so that's fine. And finally, deep learning, we do need to support multiple deep learning tools. So tools like TensorFlow, Theano, and Caffe are the popular ones. Now, if you track the evolution of programming languages and how they've evolved, there are certainly two independent dimensions. There's performance and there's productivity. The HPC community early on decided that we would not leave any flop behind, right? So it's all about performance. And if you need to write assembly code, so be it. So certainly, I think C, Fortran, assembly are right off in this corner where it's all about performance and very little about productivity. Languages like C++, I guess, have helped in terms of perhaps improving software engineering practices. If you look at the data science community, they've started off in a very, very different world. They really maybe had no performance expectations coming in, and all they cared about was productivity. So Python and R are definitely in that camp, and maybe Spark is somewhere in between. But there is this magic quadrant off to the right where you can perhaps get high performance and high productivity. And I think the Celeste project has really tried to look at Julia and see if Julia can fit into that quadrant. We've had pushback, I think, over the course of the 3 years that we've been working on this project on, why don't you just implement it in C, right? It'll run so much faster. But we actually stuck to our guns. We started off in Julia because the statistician on the team wanted the flexibility to express a rich graphical model. And despite Julia being not up to the mark, perhaps 3 years ago, we improved it as we went along. And now we are able to get some really good performance. So I think we do believe that Julia is a really promising candidate to be in this in the top right in this figure. So I guess if you forget everything else from this talk and just need to remember 4 points, this is what the team has accomplished in the last 3 years. So Celeste is the first Julia application to exceed 1 petaflop performance. And we've been now able to run on 9,300 KNL nodes. We used 1.3 million threads on 650,000 KNL cores. To the best of our knowledge, this is the most extreme scaling example for Julia. Now, we're not computing the value of pi, of course, when we run at scale. So there is a real science problem. And essentially what we did was to take most of the SDSS data set, and we processed it all in 15 minutes. So this is not batch processing where you take a data set and then slowly make your way over a period of months through the entire thing. We load it up all in memory, and then we process it all in one shot. So over the course of this job, we actually loaded up and analyzed 178 terabytes of data. So again, people throw around the word big data a lot, but really, if you think about a single job and processing a data set that's in the order of hundreds of terabytes, not many people can pull that off. And to pull it off in Julia code, I think that's a first-time accomplishment. At this scale, we did end up analyzing over 188 million stars and galaxies. And we produced the first comprehensive catalog of these visible objects with state-of-the-art parameter estimates, but also uncertainty estimates. And the uncertainty estimates are used by our astronomer colleagues to do some follow-up analysis. For the statisticians in the audience, this is the largest demonstration of variational inference at scale. Before this work, variational inference had only been applied to problems that were 2 orders of magnitude lower than where Celeste is right now. So we extracted about 8 billion parameters in this problem. And variational inference has frankly never been scaled to this level before. So I think, I've sort of been migrating, personally, I've just been migrating away from technical work to more of a managerial role. And for me, I think it's no longer about numbers and sizes of data sets. It's all about the team. And this is just a fantastic team to be affiliated with. So Jeff Regier, who's going to be talking next, has been leading a team of world-class statisticians, Ryan Giordano, Steve Howard, Andy Miller at Harvard. And then we've had John McAuliffe and Ryan Adams, both just world-class machine learning and stat experts. Thankfully, the statisticians were not off in a corner developing statistical models. They were helped by computer scientists. So in Andreas and Jared and Max Lam, we've had a lot of help in implementation. Kiran Padmani was absolutely critical in getting the multi-node scaling pieces working, so that was absolutely key. And finally, this gentleman, Keno Fischer, I guess through the course of this project, I came to know that there was a term called the Keno-verse, which is basically a universe where anything can happen in Julia. So I think it was just a privilege to have Keno on the team and just see him pull off this accomplishment. Finally, we had scientists, astronomers who had a stake in this project, and Debbie and Rollin, who's right here, and David Schlegel. They were crucial in formulating the science problem and making sure that the results of this investigation are actually useful for the astronomy community. All right, so I'm going to stop right there, and I guess Jeff is going to walk you through the science goals and also the statistical inference procedure.
Thanks very much, Prabhat. So I'll walk us through the project goals first. And first, as Prabhat mentioned, we're aiming to catalog all the galaxies and stars that are visible through the current generation of telescopes, but as well also the next generation of telescopes. The current generation of telescopes produce quite a bit of data, but the next generation will produce orders of magnitude more, so 17 terabytes of images nightly. Just a second. Yeah, our second goal is to produce a statistical model for this problem. So to date, it's been handled largely by heuristics, for loops that iterate through the pixels and look for bright spots. We're proposing a fully generative model or forward model for this problem. The third goal is to identify promising galaxies for spectrographic targeting, and this is of interest to astronomers. It'll help us to better understand dark energy and also the shape of the universe. And then finally, we wanted to develop an extensible model that will that we can extend to find supernova and also detect near-Earth asteroids. Problems with this?
We're
Back? All right. OK. So here's a sample astronomical image. This is from the Sloan Digital Sky Survey. It's both stars and galaxies, and we want to identify all the stars and galaxies in this image and also characterize them, so things like their brightness and their colors. And we want to determine whether they're stars and galaxies. In the case of galaxies, we want to determine the morphology, also the shape and scale and axis ratio and so forth. And we have a huge collection of images like this. This is maybe a more typical image from our data set. This is a quarter square degree of the sky. We have 10,000 different detections, or stars and galaxies in this image. And in the whole SDSS data set, there are 40,000 images like this. Every star and galaxy has parameters that need to be optimized in order to determine its colors and properties and so forth. We're particularly concerned about faint stars and galaxies, because those are the ones that are hardest. So for the galaxy in the top right there, it's kind of easy to say that it's got an angle that's, you can get its angle pretty easily within a couple degrees. But that source that's circled there, it's quite ambiguous whether it's a star or galaxy. And so we want to not only come with good point estimates for that star or galaxy, we also want to characterize our uncertainty about our predictions. And we want the uncertainty to be kind of calibrated. And this comes to us pretty naturally from a Bayesian model. So our approach is based on graphical models, which are just a way to represent graphically a statistical model. Here I have 3 random variables, and the graph tells you how to factorize this probability distribution. So it's a joint probability distribution over A, B, and C, and it has this factorization based on the graph. And if you're not familiar with this notation, you can still follow the subsequent slides, but this is just a brief reminder if you are familiar with it. So typically with graphical models, we want a condition on one of the 3 random variables. We denote that with shading here. And so in this case, C is an observed random variable. In our case, this is going to be the images themselves, the data. But when you condition on the observed data, you're then interested in the problem of determining the distribution of A and B. So we call the distribution of A and B the posterior in this case, and it's proportional to the likelihood times the prior. So here's our actual graphical model, rather than a toy example. The light source, at the bottom we have the images, and there are n of them in this data set. Each image is made up of m pixels, and the pixels' values, their intensities, are denoted x and m. X and m is a count, an integer, and it describes the number of photons that have traveled through the telescope and then been recorded by that pixel on the CCD. So it's an integer. We model it as a Poisson random variable with kind of an unknown rate, or a rate that's determined by the latent variables in the catalog. And so up top we have the astronomical catalog, which is the quantity we're trying to get a handle on. The astronomical catalog has variables like a sub s, which is a Bernoulli random variable. It indicates whether a particular light source is a star or a galaxy. R sub s is the brightness in at a particular wavelength. And so these are all unknown. It's just we're proposing a model right now, and we're going to infer them later. But we're just proposing the model at this point. C sub s is a vector of the colors of the light source. Mu sub s is the location of the light source. And so we want to determine that very accurately. And then finally, phi sub s is a vector that has all these properties for galaxies, so things like morphology and scale and so forth. And there are s of these light sources in our catalog. And you'll notice there are these prior variables here, these priors on all the latent random variables. And so I'll talk briefly about the priors, then about the likelihood. So the priors, for color anyway, come from a large existing catalog of data. We're not the first to build catalogs of stars and galaxies. So we can get a good idea of what stars and galaxies look like in color space, what their colors are. And what you see here, this is sort of a two-dimensional slice of color space. Color space for us is four-dimensional, but this is a two-dimensional slice. And you'll see that stars kind of inhabit this one-dimensional manifold of color space, whereas galaxies inhabit a much wider swath of colors. Galaxies can take on a much wider range of colors, in other words, whereas stars, they inhabit this one-dimensional subspace because this is basically indexed by their surface temperature. So this is a feature we can use to discriminate between stars and galaxies, and it falls out pretty naturally from the Bayesian formulation of the model, where we just put priors and unknown random variables. And so we're also going to use spatial characteristics to distinguish between stars and galaxies, but color is something we can use because of this graphical model. So that's the description of the prior. The likelihood is the probability that matches any given catalog or a fixed catalog to the images, or the probability of any particular image in the model. I'm not going to describe it in terms of equations, but just sort of intuitively, in this model we model stars as points in the sky, and that's because those stars are closer to us than galaxies. Their radius is so much smaller in relation to the distance that it's a pretty good assumption to model stars as sort of infinitely small points. Galaxies farther, but they're much larger, and so we do have to model their spatial characteristics. And for galaxies, we model that with a mixture of bivariate Gaussian densities. We may use variational autoencoders in the future, but bivariate Gaussian densities works reasonably well with enough Gaussians. So this is the model before it's viewed. But to model how the galaxies and stars actually look when they're viewed, you need something called the point spread function. And over here on the right, I have a picture of a lot of stars. And you notice these look nothing like infinitely small dots. They're each at least 10 pixels in width and so forth. And that's known as point spread. Point spread happens for a couple of reasons. The atmosphere blurs what stars and galaxies look like. So that's one thing. And you also need these spikes. These are called diffraction spikes, and these come from the telescope. They're in there by design, actually. It helps us to have some point spread in some cases. And so we model the point spread function as a mixture of Gaussians as well, and then it's a convolution operation to determine sort of from what the stars look like without the point spread function to what they look like through a telescope. Finally, our catalog is all in terms of physical units, so things like magnitude and so forth, not in terms of the number of photons that actually strike the image. So we get sort of calibration constants. At this point from a pipeline, also background radiation. There's light pollution, but then also there's just like a lot of radiation in the universe that isn't attributed to any star or galaxy. So those are things we have to account for. We get them presently from a pipeline, but we'd like in the future to learn them sort of all within our model. So sort of end-to-end type learning, where you give us the raw data and we output a catalog. And then finally, so we're studying the static universe, which sort of, it's a good model to think that it doesn't change over human timescales. Nonetheless, if you take a photo of the exact same region of the sky 2 different times, you'll see different numbers of photons recorded by the image. And that's just due to Poisson. It's randomness that's well modeled by a Poisson distribution. So the mean for a particular pixel may be 750. Maybe sometimes you'll see 760 photons. Maybe sometimes you'll see 740. But this is nicely modeled with a Poisson distribution. So it's a pretty reasonable assumption. So now the model's specified. I've told you about the prior. I've told you about the likelihood. That means the posterior, it's specified, but it doesn't mean we can get a handle on it. A standard way to determine the posterior, so the textbook way, is to apply Bayes' rule. We have our latent random variables here kind of bundled together and called theta. Capital theta given x is the quantity we're interested in. This is the distribution of the catalog. The numerator in Bayes' rule is all tractable. The first term, or first factor rather, is probability of x given theta. And that's just the likelihood, which is what we specified, and that's readily computable. Probability of theta is also readily computable. That's the prior distribution. It's this denominator that's a problem, probability of x. To get a handle on this, you'd have to do a high-dimensional integral, and that's going to be intractable in general. So we're not going to be able to apply Bayes' rule, and this is a pretty standard situation for most graphical models. I mean, all but the simplest or graphical models. So what a lot of people do is MCMC. But we have a huge amount of data, and so we're looking to do something faster, and variational inference can be orders of magnitude faster, and we need that. With variational inference, you approximate the posterior, the quantity we'd like to know, with a distribution from a family, and you try to find the member of that family that minimizes the KL divergence between the approximation and the actual posterior distribution. And because of some mathematics, the denominators in this Bayes the denominator here cancels out between the distributions, so you can do this minimization without actually determining the marginal probability of the data, P of x. If your class of approximating distributions can be indexed by real numbers, real values, such as in the case if you were to do like a multivariate normal distribution for your approximating family, and then index it with the mean and standard deviation, then you'd be left with a numerical optimization problem. And so what variational inference does in that case is it converts a problem about distributions to a problem of numerical optimization. Numerical optimization is something that there are a lot of tools to solve. That said, we still get a very complicated objective function. And for implementing this kind of objective function, I mean, actually, if it were expanded out, we could go a couple more slides. We not only implement the objective function, but also do both derivatives, gradients rather, and Hessians. So we do Hessians with primarily with manual differentiation, a little bit of automatic differentiation for certain parts that aren't computationally intensive. But in a language besides Julia, it would be quite tedious to get this done. I mean, it's tedious regardless, but it's much easier in Julia, where the syntax of the language looks a lot like math. So we do solve this optimization problem, and I'll first show some results on small data before talking about the optimization procedure that works at scale. On the left, we have an image of about 3 stars. And then on the right, we have our reconstruction of that image. So this is the mean of our approximate posterior distribution on the right. And they look pretty similar, and that's the point. You'd want them to look pretty similar. The left is 51 by 51 pixels, so about 2,000 values, whereas on the right, we're summarizing each star with 44 numbers. So to some extent, it's a data compression problem to determine a catalog from image, kind of a lossy data compression problem. For validation, we also worked with a particular region of the sky known as Stripe 82. And Stripe 82 is unique in that it's been imaged a lot more than most other regions of the sky. So there's no ground truth in astronomy, but we can get something close to ground truth to score ourselves in Stripe 82. What we do is with maybe all 50 copies or so of the data on Stripe 82, we run the existing standard practice photo on that data. And with 50 copies of the data superimposed on each other, things that are dim, like dim stars or galaxies, just sort of pop out, and it's obvious what the answers are. So we use that as our ground truth for this kind of comparison, and this is a table of the average error. Then we run Photo and Celeste on 1 copy of the data and compare it to how Photo does in all 50 copies. And basically, sort of like across the board, we're outperforming the current standard practice for determining different quantities. In terms of position, Photo's off by about a third of a pixel, and Celeste is off by about a quarter of a pixel. And so it's statistically significant. We did this on a sample of 600 or so stars from Stripe 82. But it's also practical significance to astronomers, a reduction of that magnitude. On brightness, about a third reduction. For color, we did particularly well, usually cutting the error rate on each of these colors down by over 50%. Profile is whether it's a spiral or exponential galaxy. We had a pretty big reduction there. Axis ratio is if we modeled the galaxy as an ellipse, the ratio of its smaller axis to its larger axis, and we cut down the error there too. Scale, we decrease it by a lot. There's an outlier that prevents statistical significance in this sample, but it's a pretty good reduction. On angle, the old system is off by about 22 degrees, and we're off by about 17 degrees on average for determining the rotation of galaxies. So good results, and we wanted to scale this to all of SDSS rather than just a small sample. We propose a technique that minimizes an objective function where the objective function is defined in terms of all the data, and we want to use all the nodes of a large supercomputer to find this stationary point, so where the gradient of our objective function is 0. To do that, we have a multi-level scheme. And the first is that we divide the sky into blocks, and we have different nodes working in parallel on optimizing the blocks. So here I have sort of A1 through A9 and B1 through B16. These are all different chunks of work. What we're doing at the top level is called block coordinate ascent, and it's a serial algorithm. It says you optimize one block, and then you optimize the next block of parameters. However, with this configuration, we can optimize A1 and A3, for example, in parallel, and it'll be equivalent to a serial algorithm. So it'll nonetheless preserve the convergence guarantees of a block coordinate descent. The second step of the algorithm is on the node level. There's still a lot of parallelism, quite a few threads. The KNL nodes have around 130 threads that we want to keep busy. And in this case, we have light sources that overlap, and we're doing sort of block coordinate ascent again. So in this case, if you optimize 1 and 2 simultaneously, you'd be taking a gradient step based on the old parameters for both, and you wouldn't necessarily get convergence. Instead, we have kind of a locking scheme where you can optimize 1, 3, and 5 simultaneously, and 2 and 4 simultaneously. And in practice, we're able to keep the threads busy. So the name of the game here is to keep all the threads working as much as possible. The images we send out usually have many more than 5 light sources. So there's usually work available for the threads. And then the final step of our optimization procedure, or level, I should say, of the optimization procedure, is using Newton's method with a trust region constraint. It's a non-convex problem, so that's where the trust region constraint comes in. Newton's method is a second-order method that converges very fast in practice. It converges in sort of tens of iterations, whereas something like stochastic gradient descent or gradient descent would take thousands or tens of thousands or hundreds of thousands of iterations to converge. So this is really essential for getting convergence in a reasonable amount of time, and we couldn't do Newton's method without having implemented the Hessian ourselves. So yeah, I'll talk. The target platform and what we ran on is Cori Phase 2. Cori Phase 2 has 9,300 nodes, and each node has 68 cores. So a lot of parallelism, and for each core, we run 2 threads in order to fully utilize it. Each core can do 8 instructions simultaneously if they're the same instruction. So this is like SIMD-style parallelism. If you do fuse multiply adds as those instructions, and it's not always possible to do fuse multiply adds, but when you can, that counts as two instructions per cycle, both an add and a multiply. And then also FMAs have this property that you can do 2 per cycle. And then finally, the Cori Phase 2, the chips are running at 1.4 gigahertz. So slower than a desktop, but a ton of parallelism. And it all adds up to 30 petaflops as the peak sort of theoretical performance. We achieve 1.54 petaflops in native Julia, and it's this first time sort of any language besides, I think, assembly, C++, C, or Fortran have reached over a petaflop. So we're pretty excited about that. That was using 1.3 million threads and over 500,000 cores. SDSS is this huge data set, 55 terabytes. And we load it 3 times, so it's like 178 terabytes of loading in total. But in 14.6 minutes, we've loaded SDSS and processed it and optimized sort of 188 million stars and galaxies. And then sort of one other measure of the scaling is that in early March, when Keno and members of Julia Computing sort of joined the project, and a couple members from MIT, we had a benchmark that ran in 320 seconds. And that runtime was lowered to 17 seconds by mid-April. So pretty outstanding reduction in runtime. And I should mention, it wasn't like it wasn't optimized at the beginning. I mean, the types were pretty stable. We weren't allocating a lot of extra memory. So Keno in particular worked quite a bit of magic to make this happen. I learned a lot about scaling Julia code from him, and he's talking next, so you can too. And he's up now. Please give him a warm welcome. Thank you.
Is it higher or? It's too low. All right. All right. Sorry, we have 2 microphones, one for the room, one for the video. All right. Can people hear me? I know the audio has been. Yes? Good? Good? Great. All right. Yeah. All right. So the first thing I want to talk about actually has nothing to do with Julia, but I felt was worth pointing out anyway, which is that we're doing a very, very large scale data analysis problem. And with any such problem, I/O, getting the data to the nodes, is a significant challenge, and we had to do quite a bit of work to actually make this happen. So Prabhat mentioned at the beginning when he introduced Cori that Cori does have this SSD array attached to the high-speed network, and this is a figure that I just stole from the NERSC website. The topology isn't quite right, but it sort of gives the idea, which is that there's a whole bunch of compute nodes, and then sort of off to the side, still attached to the fabric, there's a bunch of SSDs, and then sort of further away there is a bunch of spinning disks for bulk storage. Now these SSDs are specified at giving you 1.2 terabytes per second of data throughput, which we thought was just about okay, because it turns out for the full-scale problem, you end up loading about a petabyte of data from disk. The data set is smaller, but sort of due to the scale, due to the division that we do, multiple nodes have to load the same data. So even though the data set is only 55 terabytes, sort of the total amount of data that goes over the network is a petabyte for the full-scale problem. But it turns out that we were sort of the first ones to actually attempt to do this kind of large-scale I/O. So we had some problems. The first one being SDSS is several million files, which the file system didn't handle really well. So it was fine with a couple of files, but if we tried to open millions of files in parallel, it would sort of give up on us and hang up and degrade the system for the entire center. So what we ended up doing was actually repackage the entire data set into 55 1 terabyte files, which the file system was a lot happier with. Then we implemented that a loading for that in Julia and put that on the SSD, and with that we got pretty good data throughput of about 400 or so gigabytes per second, which is not quite 1.2 terabytes, but it was enough for the problem that we were doing. In the future, we're hoping to leverage the network a little more, but the last time we had tried that, we brought down the network with all the data traffic that we were doing. So for this run, we were just running off of the SSDs. All right. So with that, let me talk about what it took to get to the kinds of performance numbers that we had in the Celeste project. So here, I wrote down the standard advice for writing high-performance Julia code, and mostly I have this slide because I'm not going to talk about any of it. And the reason for that is that essentially all of this was already done by the time we started working on Celeste. So if you follow these guidelines, and if you follow the performance guidelines, if you have type-stable code, if you are sort of careful about your memory allocations, and if you use the various profiling tools to give you opportunities of where to do this, the code that Julia will generate for you is quite good. It's following these guidelines. If you were to compare it to another language, if you were to compare sort of decently optimized C and C++ code to Julia that follows these guidelines, you'd find about the same level of performance. So this is sort of the table stakes on which we can start thinking about optimizations for really, really high performance. And that's what I'm going to talk about for the rest of the talk. So these are the prerequisites. OK. So let's talk about performance. And this is a bit of an intimidating slide, but what I did here is I went into the code base, and the majority of the hot code in Celeste is computing this Hessian of this really, really large objective function that Jeff talked about a couple slides earlier. And this is one multiply sort of deep down in the 2,000 lines of code that do this. And what I did on the slide is I went back to the entry point of the evaluation procedure and sort of wrote down all the for loops that I could find in the way. And the reason this is important is because when we think about single thread optimization, the name of the game is finding which instructions can be executed in parallel and putting them in a vector and using SIMD and using the SIMD units. So I looked at this, and the ILP we were able to find in sort of the innermost function was about 10 to 12 instructions, which is actually pretty good. I mean, it's sort of standard for scientific codes, but for general purpose codes, it's usually lower than that.
What is ILP?
Oh, it's an instruction level parallelism. So basically that means, if I have one instruction and then I do a second instruction, but the second instruction needs to use the result from the first instruction, I can't do those in parallel. So ILP is a measure of how many instructions do not depend on anything previously. So in theory, I could, if I had a data flow machine, with infinitely wide, units, how many of them could I do in parallel? So, rough numbers, but we're looking at about 10 to 20 for the innermost function. And then if we want to go much above that, we sort of need to go 3 levels of function calls higher to find ILP of about 800. And when I say 3 function calls higher, that means that the if we were to write down all the code, this is where the 2,000 lines of code are. So we're basically almost at the top of this very big optimization, of this very big evaluation of the objective function. So why is this important? Well, we wanted to take maximum advantage of all the flops on the machine. So let's look at sort of the theoretical maximum that we could possibly be doing. As was mentioned, we can do 2 FMAs per cycle. On Haswell, we have a latency of 5 cycles. That means the result of a previous instruction is only available 5 cycles later. And we have a vector with width of 4. So if we really, really wanted maximum ILP, we would need maximum throughput, we'd need an ILP of 40. On KNL, it's even worse because the vector units are wider, the latency is longer, and sort of for human factors, it's significantly lower clocked. So if you're waiting for your results, you care about max throughput perhaps more than you would on Haswell. So looking at this again, 10 to 20 was kind of okay on Haswell. That's a quarter to half max throughput, theoretically achievable, and that's pretty good. Even hand-coded BLAS does not get max throughput because it needs to do other things other than just FMAs. But for KNL, that's sort of too low. So for KNL, 10 to 20 doesn't really cut it. So what we had to do for KNL was actually go to those 3 loops up there and essentially inline through those 3 levels of function calls, inline 2,000 lines of Julia source code. It ended up about 30,000 assembly instructions, put them all in one big scalar inner loop, and then vectorize vectorize across that. And as you can imagine, vectorizing, convincing a compiler to vectorize over 2,000 lines of source code or 30,000 instructions, either at the LLVM or at the x86 level, they're sort of comparable in magnitude. You need to give the compiler a lot of assurances that it's allowed to actually do this. So a lot of the time that I spent on this project was spent on improving Julia and improving LLVM to give it the license to perform this vectorization. So here on the slide, I sort of wrote down all the things that I could remember doing for this project. Unfortunately, I do have to say that at the moment, most of these are not in Julia Master, mostly because we had a month to do this, and I'm a lot faster at writing hacky code than production-ready code. But sort of since the project wrapped up, I've been working on getting these into both Julia and LLVM. You might have seen the new GC root placement pass merge just a couple of days ago. So look forward to seeing some of these improvements make their way onto Julia Master slowly. And hopefully by the time we're at 1.0, we could have done Celeste without any compiler changes. But again, I'm also not going to talk about any of these in detail. You can find the details on GitHub, but I really want to talk about what we did in Julia and how Julia was able to help us achieve this kind of performance on the supercomputer. So sort of the first and simplest example of something that helped the compiler out a lot is using the static arrays package. The static arrays package allows you to have A, immutable, vectors and matrices, and B, statically annotate the size of your vectors and matrices. And this is enormously helpful for the compiler. If the compiler knows how big your matrices are, it can do unrolling of loops that access the matrices. It can sort of vectorize several columns at once because it knows they're next to each other in memory. And it's enormously helpful for the compiler to have this information. And I want to point out that all of this is applicable not just to Julia, but to every other language as well. So if you're familiar with Eigen in C++, it sort of has similar facilities for giving statically the size of arrays, which in that case is also very helpful for the compiler. So this is sort of the simplest example, and I have two others that I thought were very cool and I want to highlight, but there was of course more that we did. So the next thing we did is something that is very classical, a very classical example of an optimization that you do for high performance codes. So here I put up a simple figure of memory access in a scalar loop. So the loop has 4 operations, and I show 4 iterations of the loop. And for the scalar loop, the memory is sort of very nice. It's sort of one after the other, very sequenced. But if you naively run the vectorizer on that, you get all kinds of crisscross lines, as you can see in the middle figure. And crisscross lines are expensive. So some architectures, including modern x86, have some hardware support for doing the crisscross loads in hardware with just one instruction. But those still generally tend to be slower than just loading a block in memory at once. And if you happen to have crisscross loads that are beyond the capabilities of what the hardware can sort of do for free for you when loading, you end up with thousands of vector shuffles in your code, which reduce your performance. So the first thing that we noticed after our 2000 source line loop finally vectorized was that some of the input arrays had very much this problem, and LLVM generated several thousand lines of vector shuffles for us to get them back in line. So that obviously doesn't look very nice when looking at the assembly, which is my primary problem, but also it doesn't perform very well. So the solution to that is very simple, which is that you can statically rearrange not just the computation but also the memory to make the accesses aligned. So what you do is you instead of having a structure with a bunch of elements and then an array of those, you just do a bunch of arrays with sort of the memory optimally laid out for the code that's going to be accessing them. So that's a very, very classical transformation. But in Julia, it's extremely easy to do thanks to the struct of arrays package. We had to modify it slightly because the type that we had was sort of deeply nested. It contained a bunch of static matrices and static vectors and several nested types. But once we updated the package, all it took was one line change in this data structure to tell it, instead of a matrix of galaxy cache components, we'd like to have a struct of arrays of galaxy cache components. And no other changes to the code were required. So this is sort of a very simple example of why I think Julia is actually a great language for writing really high performance codes. Because once you get past the initial problem of just generating the code, there's higher level transformations, for example, such data structure transformations that become very, very important. And in Julia, they're very easy to do thanks to being able to do reflection on types as well as metaprogramming. So that was sort of a very simple and general example. Here's another example which is very much in the same vein, but it was very specific to Celeste. So what I'm plotting here is actually the Hessian of that objective function that we've been talking about. And black represents zeros in this matrix, and each color corresponds to one inner loop in this computation. So a couple of things to notice. We have a lot of zeros. In fact, a couple of parameters are not used at all in this particularly hot part of the code that we're looking at. Also, sort of the memory accesses within a loop jump all over the place, which is A, bad for vectorization because it, again, can't load them as a chunk, and B, bad for the cache hierarchy because it doesn't know to prefetch the next values that you're accessing. So you end up going to a higher level cache, and you pay the penalties. Memory goes down columns as a standard for Julia arrays. Okay, so what can we do about this in Julia to make it a lot faster? Well, let's look at how this actually looks like in the code. So I just took the top line is a very simple example of one line in this evaluation of the Hessian, and IDS.U is an array of indices into the matrix where the relevant data is stored. So in this case, IDS.U is just 1 and 2. So it's the first two parameters in this matrix. So what can we do? Well, we have multiple dispatch. So instead of making an array of indices, let's just make IDS.U an object and use multiple dispatch to do the mapping of, well, these are the indices to here's where they're stored. And conceptually, the way this works is, you have a getIndex function. If you index into a matrix, it just does, the thing it did before, namely indexing with 1 and 2. But, now you use multiple dispatch, and you can basically write down whatever data structure you want and write an appropriate indexing method to pull out the data from wherever it is stored. So this is sort of a way to separate the semantics of the operation from the underlying representation of the data in memory. And this is very important for retaining the flexibility to change it. So it looks the same to Jeff. I didn't have to rewrite the 2,000 lines of code such that Jeff could never change it again. But from the machine's point of view, it now looks like this. All the black squares are gone. There's no stored zeros anymore. And so this is, just to point it out, this is no longer a matrix. It just, it's one big struct in memory. The slide just isn't long enough to put it all in one row. But sort of all the memory accesses are now next to each other. No zeros are stored anymore. It's about 4 times smaller than it was originally. And that turned out to be hugely important because this structure fits in L1 cache versus the original matrix does not. So you get significant improvements because of that. And again, this was a one-line change to the data structure. Now I actually wrote about 200 lines of code to, given a specification of which parameters there are, automatically generate all of these indexing methods. So we didn't have to write them out, but we wrote a small Julia package, about 200 lines of code, that, given an arbitrary indexing pattern and an arbitrary data structure, generates these indexing methods. So, a little bit of work, but, no fundamental changes to the compiler, just 200 lines of Julia, and we were able to do a very, very complex data structure transformation to improve performance. So those are sort of the kinds of takeaways that I wanted to give with these 3 examples. I didn't talk about getting to good, well-performing Julia code in the first place because I think that is relatively well understood. But what I wanted to show you is that Julia can make some sort of very advanced transformations which are very useful for performance very easy. And sort of in my mind, the reason why this works is because Julia allows you to separate the semantics from the representation. So you can, write your code as you would usually, and if you want to prototype it or if you're just starting a project, just write it in whatever way seems most natural to you, knowing that Julia is powerful enough to change the data structure under the hood later if it needs to. So this is very easy in Julia. We were able to do a very, very sophisticated transformation in about 200 lines of Julia code. We could split it out in a separate package to make it more generally useful. we had very large performance gains. So these three transformations that I talked to you about were easily responsible for 5 to 10x improvement in the final performance. And lastly, since we didn't have to rewrite any of the code, it made it very easy to switch back and forth between the data structures to debug, did I make a mistake in the algorithm, or did I make a mistake in the way I represent this? So sort of retaining the flexibility to go back to a known representation of the data and compare it to what the data looked like in a previous version of the code turned out to be immensely helpful in writing this application. So sort of to recap the major points of this project, it's the first Julia application to exceed a petaflop. We think it's probably the first application written in something other than C, C++, Fortran, or assembly to exceed a petaflop. We had very sophisticated single node optimizations. We were able to scale effectively to 9,300 nodes, 650,000 cores, 1.3 million threads. We solved a pretty significant data problem by loading the SDSS data set. We loaded 178 terabytes in 15 minutes. And as was mentioned earlier, it's sort of the first comprehensive catalog with state-of-the-art estimates for both the parameters as well as the uncertainties. Lastly, sort of from the Julia perspective, I feel like that with all these compiler optimizations, Julia generates the quality of native code that is required for HPC applications and can compete with some of these incumbent languages in this domain. And it's getting better. We have thoughts and we have plans for improving this further. And more importantly, we have plans for making all of this easy and automatic, such that sort of some of the hoops we had to jump through to make this first petaflop scale application happen, for the next petaflop scale application for anybody in this audience, it'll just happen automatically. All right. And with that, Jeff asked me to give a shout out in this room. They're hiring Julia programmers to work on the next generation of Celeste. Email him at that address and reach out if you're interested. And I think we have some time for questions, maybe, Andreas? All right. 1 question, 2 questions? Thank you very much.